Okay, let's dive right into this explainer. Today, we're taking on the infamous LeetCode problem, Invert Binary Tree. But instead of just rushing straight to the code and trying to memorize some solution, we're going to do something a little different. We're going to actually discover the answer together through a guided Socratic dialogue. It's kind of like a logic journey, where we'll just strip away all our assumptions step by step.
So can you solve a complex algorithm just by asking the right questions? Well, we're going to play the roles of mentor and mentee today to figure that out. We'll use a series of logical checkpoints to prove that, honestly, asking the right questions is just as crucial as writing the code itself. In a real technical interview, it's your thought process that truly matters. By questioning our own first instincts, we can literally transform a really daunting algorithm into something, well, incredibly simple.
All right, Section 1, the core observation. Our journey kicks off with a solid initial look at what this algorithm actually requires us to do. Every great solution starts with simply stating the obvious and building from there.
Looking at this quote here, our mentee makes a really sharp initial observation. They correctly spot that, fundamentally, to invert a binary tree, we just need to swap the left and right sides. Simple enough, right? But catch that second sentence. The mentee just assumes the process absolutely must start at the very bottom, at the deepest subtrees, and then work its way up to the root. It's a supernatural assumption to make, but is it actually correct?
This brings us to Section 2, challenging the order. You see, a good mentor doesn't just flat out say, "You're wrong" when you make an assumption. They make you prove it to yourself.
So, the mentor gently pokes at the logic. They ask, walk me through, step by step, what happens if you swap the root's children first before touching anything deeper? Does that break anything? Basically, they're testing if that bottom-up approach is strictly necessary. Imagine a tiny tree, just a root with a left and right child, and swap those first before digging any deeper. Does the whole tree break? Does the inversion fail?
And we quickly realize, no way. Swapping the top subtrees first doesn't break a thing. You can absolutely swap the top and then just swap the deeper branches later. The real game changer here is realizing that the order doesn't actually matter. The swap is what we call a local decision at each node. It completely ignores what's already happened elsewhere in the tree. And man, this realization drastically simplifies how we're going to approach the whole problem.
Moving right along to Section 3, finding the base case. Let's see how this local decision builds into an actual recursive algorithm.
Now, if we're making a local decision at every single node, recursion is definitely the right tool for the job. But recursion always needs a stopping point, right? So, our mentee proposes a base condition. Stop when both child nodes are leaf nodes, reaching the leaves, doing the swap, and returning the root node. It sounds incredibly logical on the surface, but as we know, logic always needs a good stress test.
So the mentor brilliantly stress tests this with a specific concrete example. They say, okay, let's look at an unbalanced tree. Imagine a node, let's call it node 2, that isn't a leaf, but it doesn't have 2 leaf children either. It only has a left child, say node 4, and 0 right child. If our base condition demands that both children be leaves, this specific node would literally break our algorithm. Our recursion would just panic. It wouldn't know what to do.
And bam, this brings us right to a major trap, assuming all trees are perfectly balanced or full. The mentee admits they totally fell for it. Catching this assumption trap early on is absolutely vital, because let's be real, LeetCode trees and actual real-world data structures are almost never guaranteed to be perfectly balanced. You absolutely have to account for those messy, lopsided edges.
So, by realizing the tree might be unbalanced or just completely missing children, we arrive at a vastly superior and honestly much simpler base condition. We just check if the current node or head is none. If you hit a none, just return none. That's it. No need to overcomplicate things by checking for leaf status. Just stop when you hit the bottom of any path, whether it's super short or super long.
Okay, Section 4, tracing the algorithm. With our new bulletproof base condition in hand, we need to make sure the recursion actually bottoms out correctly. We've got the theory, now let's see it in action. Tracking the state of a single unbalanced tree, call by call, makes the whole abstract concept of recursion highly visual and so much easier to follow. If we start up at invert 1, we swap its children, 2 and 3, and then recursively call invert on them. When we hit invert 3, which has no children, we're literally just swapping none with none and passing those nones right back down, which triggers our base case perfectly. And then at invert 2, we swap node 4 with none. It handles the whole lopsidedness without breaking a sweat.
And this trace brilliantly illustrates that our logic holds up from end to end. Cleanly inverting even an unbalanced branch works flawlessly. Look at the final result. Node 2 originally leaned to the left with node 4. Now, it leans to the right with node 4. The final shape is a true, perfect mirror of the original unbalanced tree. Pretty cool, right?
Which brings us to section 5, the Python solution. Now that we've derived the algorithm through rigorous tracing, instead of just jumping straight to the keyboard, writing the actual code is going to be incredibly straightforward.
We've done all the heavy lifting. The syntax is just the final translation. Here's the plain English version of the algorithm we just traced. Step 1, check the base case. If the node is none, return none. Step 2, swap the left and right children of the current node. Step 3, recurse on the left, then recurse on the right. Step 4, return the node. It's clean, it's highly logical, and it covers absolutely every single edge case.
But hold on. Before we reveal the final code, the mentor poses one last vital question about the order of operations. We know for sure we have to swap, and we know we have to recurse twice, but does it actually matter if we swap before we recurse or after we recurse?
Turns out, our mentee correctly deduces that the order doesn't matter here either. The swap operation simply relabels the pointers. The internal work inside each subtree is completely independent. It's totally unaffected by whether you swap the top-level pointers first or last. You're recursing on the exact same two subtrees either way, just using different pointer names. When that clicks into place, man, it is a genuine eureka moment.
And here is the final payoff. 5 elegant lines of Python code that serve as the inevitable simple conclusion to our entire Socratic dialogue. We check if not root, we execute the super clean Pythonic one-line swap for left and right, we call the function recursively on the left and right, and we finally return the root. It feels effortless, right? And that's because we systematically eliminated every single assumption that could have made it complicated in the first place.
So, as you gear up for your own coding interviews, remember that the best code really comes from testing your logic first, not just rushing to type. Always question those initial assumptions. Ask yourself, does this actually have to be bottom-up? Am I just assuming this data is perfectly balanced? By acting as your own Socratic mentor, you can unravel almost anything. So, I'll leave you with this. What complex problem will you stress test next?